Distribution of oceans and continents. Continents cover 29% of the surface of the Earth, and the remainder is under oceanic waters. The positions of the continents and the ocean bodies, as we see them in the map, have not been the same in the past. If this is so, the question arises: what were their positions in the past? Why and how do they change their positions? Continental drift. Alfred Wegener, a German meteorologist who put forth a comprehensive argument in the form of the continental drift theory in 1912. This was regarding the distribution of the oceans and the continents. According to Wegener, all the continents formed a single continental mass and mega-ocean surrounded the same. The supercontinent was named Pangaea, which meant all Earth. The mega-ocean was called Panthalassa, meaning all water. He argued that, around 200 million years ago, the supercontinent, Pangaea, began to split. Pangaea first broke into two large continental masses as Laurasia and Gondwanaland, forming the northern and southern components respectively. Subsequently, Laurasia and Gondwanaland continued to break into various smaller continents that exist today. A variety of evidence was offered in support of the continental drift. Some of these are given below. Evidence in support of the continental drift. The matching of continents, jigsaw fit. The shorelines of Africa and South America facing each other have a remarkable and unmistakable match. Both of them will fit quite perfectly. Rocks of same age across the oceans. The radiometric dating methods developed in the recent period have facilitated correlating the rock formation from different continents across the vast ocean. The belt of ancient rocks of 2,000 million years from Brazil coast matches with those from Western Africa. The earliest marine deposits along the coastline of South America and Africa are of the Jurassic Age. This suggests that the ocean did not exist prior to that time. Tillite. It is the sedimentary rock formed out of deposits of glaciers. The Gondwana system of sediments from India is known to have its counterparts in 6 different land masses of the southern hemisphere. At the base, the system has thick tillite indicating extensive and prolonged glaciation. Counterparts of this succession are found in Africa, Falkland Island, Madagascar, Antarctica and Australia besides India. Overall resemblance of the Gondwana-type sediments clearly demonstrates that these land masses had remarkably similar histories. The glacial tillite provides unambiguous evidence of paleoclimates and also of drifting of continents. Placer deposits. The occurrence of rich placer deposits of gold in the Ghana coast and the absolute absence of saucer rock in the region is an amazing fact. The gold-bearing veins are in Brazil, and it is obvious that the gold deposits of the Ghana are derived from the Brazil Plateau when the two continents lay side by side. Deposition of fossils. The skeletons and fossils of identical species are found in the southern Cape province of South Africa and Arava formations of Brazil. The two localities presently are 4,800 kilometers apart with an ocean in between them. Force for drifting. Wegener suggested that the movement responsible for the drifting of the continents was caused by pole fleeing force and tidal force. The polar fleeing force relates to the rotation of the Earth. You are aware of the fact that the Earth is not a perfect sphere. It has a bulge at the equator. This bulge is due to the rotation of the Earth. The second force that was suggested by Wegener, The tidal force is due to the attraction of the moon and the sun that develops tides in oceanic waters. Wegener believed that these forces would become effective when applied over many million years. However, most of scholars considered these forces to be totally inadequate. Post-continental drift theories. Convectional current theory. Arthur Holmes in 1930s discussed the possibility of convection currents operating in the mantle portion. These currents are generated due to radioactive elements causing thermal differences in the mantle portion. Holmes argued that there exists a system of such currents in the entire mantle portion. This was an attempt to provide an explanation to the issue of force, on the basis of which contemporary scientists discarded the continental drift theory. Mapping of the ocean floor. Detailed research of the ocean configuration revealed that the ocean floor is not just a vast plain but it is full of relief. The mapping of oceanic floor in the post-war period provided a detailed picture of the ocean relief, and indicated the existence of submerged mountain ranges as well as deep trenches, mostly located closer to the continent margins. The mid-oceanic ridges were found to be most active in terms of volcanic eruptions. The dating of the rocks from the oceanic crust revealed the fact that they are much younger than the continental areas. Rocks on either side of the crest of oceanic ridges and having equidistant locations from the crest were found to have remarkable similarities both in terms of their constituents and their age. Ocean floor configuration. The ocean floor may be segmented into three major divisions based on the depth as well as the forms of relief. These divisions are continental margins, deep-sea basins and mid-ocean ridges. Continental margins. These form the transition between continental shores and deep-sea basins. They include continental shelf, continental slope, continental rise and deep oceanic trenches. Of these, the deep oceanic trenches are the areas which are of considerable interest insofar as the distribution of oceans and continents is concerned. Abyssal plains. These are extensive plains that lie between the continental margins and mid-oceanic ridges. An abyssal plain is an underwater plain on the deep ocean floor, usually found at depths between 3,000 and 6,000 meters. The abyssal plains are the areas where the continental sediments that move beyond the margins get deposited. Abyssal plains cover more than 50% of the Earth's surface. Mid-oceanic ridges. This forms an interconnected chain of mountain system within the ocean. It is the longest mountain chain on the surface of the Earth, though submerged under the oceanic waters. It is characterized by a central rift system at the crest, a fractionated plateau and flank zone all along its length. The rift system at the crest is the zone of intense volcanic activity. In the previous chapter, you have been introduced to this type of volcanoes as mid-oceanic volcanoes. Distribution of earthquakes and volcanoes. Seismic activities and volcanoes are distributed along the line of dots in the central parts of the Atlantic Ocean, almost parallel to the coastlines. It further extends into the Indian Ocean. It bifurcates a little south of the Indian subcontinent, with one branch moving into East Africa, and the other meeting a similar line from Myanmar to New Guinea. You will notice that this line of dots coincides with the mid-oceanic ridges. The shaded belt showing another area of concentration coincides with the alpine Himalayan system and the rim of the Pacific Ocean. In general, The foci of the earthquake in the areas of mid-oceanic ridges are at shallow depths, whereas along the alpine Himalayan belt as well as the rim of the Pacific, the earthquakes are deep-seated ones. The map of volcanoes also shows a similar pattern. The rim of the Pacific is also called Rim of Fire due to the existence of active volcanoes in this area. Concept of seafloor spreading. The mapping of the ocean floor and paleomagnetic studies of rocks from oceanic regions revealed the following facts. It was realized that all along the mid-oceanic ridges, volcanic eruptions are common and they bring huge amounts of lava to the surface in this area. The rocks equidistant on either sides of the crest of mid-oceanic ridges show remarkable similarities in terms of period of formation, chemical compositions and magnetic properties. Rocks closer to the mid-oceanic ridges have normal polarity and are the youngest. The age of the rocks increases as one moves away from the crest. The ocean crust rocks are much younger than the continental rocks. The age of rocks in the oceanic crust is nowhere more than 200 million years old. Some of the continental rock formations are as old as 3,200 million years. The sediments on the ocean floor are unexpectedly very thin. Scientists were expecting, if the ocean floors were as old as the continent, to have a complete sequence of sediments for a period of much longer duration. However, nowhere was the sediment column found to be older than 200 million years. The deep trenches have deep-seated earthquake occurrences while in the mid-oceanic ridge areas, the quake foci have shallow depths. These facts and a detailed analysis of magnetic properties of the rocks on either sides of the mid-oceanic ridge known as the seafloor spreading. Constant eruptions at the crest of oceanic ridges cause the rupture of the oceanic crust and the new lava wedges into it, pushing the oceanic crust on either side. The ocean floor thus spreads. The younger age of the oceanic crust as well as the fact that the spreading of one ocean does not cause the shrinking of the other. But the ocean floor that gets pushed due to volcanic eruptions at the crest sinks down at the oceanic trenches and gets consumed.